Mars, a world of mystery, of possibility, and of relentless ambition. For over 6 decades, humans have looked to this distant red planet, sending probes, landers, and rovers in a quest to uncover its secrets. Some missions have been triumphs, changing our understanding of the cosmos, while others have ended in heartbreaking failure, lost to the void. But each attempt has brought us one step closer to our ultimate dream, setting foot on Mars. This is the story of every mission we have sent to the Red Planet. Our journey into Martian exploration begins with the very first attempts, a testament to humanity's early ambition to reach beyond Earth. In 1960, the Soviet Union, a pioneer in the space race, embarked on a bold endeavor to send the first spacecraft to Mars. They launched Marsnik 1, followed shortly after by Marsnik 2. Both missions were designed as flyby attempts, aiming to gather initial data and images of the red planet as they passed. However, these early missions encountered the formidable challenges inherent in the nascent era of spaceflight. Tragically, both Marsnik 1 and Marsnik 2 suffered launch failures. These setbacks underscored the immense technical hurdles that had to be overcome in order to successfully navigate interplanetary space. The failures, while disappointing, provided valuable lessons and highlighted the complexity of rocket technology and space navigation, paving the way for future, more successful Martian endeavors. They served as a stark reminder of the risks and difficulties associated with pushing the boundaries of human exploration. Following the initial setbacks of the Marsnik missions, the Soviet Union persisted in its quest to reach Mars. In October 1962, they launched Sputnik 22, another ambitious attempt to explore the Red Planet. This mission, while shrouded in some historical ambiguity, was likely designed to either orbit Mars or perform a flyby, gathering crucial data about the planet's environment. Unfortunately, Sputnik 22 also fell victim to the inherent challenges of early space exploration. The spacecraft suffered a launch failure, preventing it from escaping Earth's gravitational pull. Instead of embarking on its intended journey to Mars, Sputnik 22 disintegrated while still in Earth orbit. Due to the secrecy surrounding the Soviet space program at the time, specific details about Sputnik 22's intended mission remain somewhat obscured. However, it's clear that the goal was a significant step forward in Martian exploration, and the failure underscored the difficulties of achieving interplanetary flight. Despite the loss, the Soviet Union continued to refine its technology and strategies, learning from each setback and pushing closer to the goal of successfully reaching Mars. Later in that same pivotal year of 1962, the Soviet Union launched Mars 1, a mission that held the promise of a significant breakthrough in Martian exploration. This probe was designed to be the first spacecraft to perform a flyby of Mars, a feat that would have marked a major milestone in human space exploration. Mars 1 achieved a crucial initial success. It successfully escaped Earth's gravitational pull and embarked on its interplanetary journey. For a period, the spacecraft transmitted valuable telemetry data back to Earth, confirming its proper functioning and providing crucial insights into the interplanetary environment. However, as Mars 1 continued its voyage towards the Red Planet, communication with the probe was abruptly lost. Tragically, this loss of communication occurred before Mars 1 could complete its planned flyby. While the mission demonstrated the Soviet Union's growing capabilities in launching spacecraft towards Mars, the inability to receive data during the crucial flyby phase meant that the scientific goals of the mission were not fully realized. Despite this setback, Mars 1's successful departure from Earth orbit and its initial data transmission represented a significant step forward, providing valuable experience for future Martian endeavors. Adding to the tumultuous year of 1962, the Soviet Union launched Sputnik 24, another attempt to reach Mars that ultimately ended in failure. Like several of its predecessors, Sputnik 24 did not manage to escape Earth's orbit, succumbing to the challenges of launch. While specific details remain somewhat unclear due to the historical context, it's believed that Sputnik 24 was likely intended to be either a Mars orbiter or a lander. This suggests a growing ambition within the Soviet space program to not only fly by Mars, but also to establish a presence in Martian orbit or even on its surface. The failure of Sputnik 24, alongside the other Soviet attempts of that year, underscores the immense difficulties of early interplanetary missions. Each launch failure, while a setback, provided valuable data and experience that contributed to the ongoing development of Soviet space technology. Despite the repeated failures, the Soviet Union's determination to explore Mars remained strong, driving them to continue refining their techniques. Zond 2 was a Soviet spacecraft launched on November 30, 1964. Its primary goals were to conduct a flyby of the planet, capture photographs of the Martian surface, and collect scientific data on interplanetary space and Mars's environment, including its magnetic field and radiation levels. Equipped with a camera and various scientific instruments, Zond 2 was intended to build on the partial success of Mars 1, an earlier Soviet probe. However, the mission encountered significant challenges. Shortly after launch, one of its solar panels failed to deploy fully, reducing power generation. Communication with the spacecraft was lost in May 1965 before it could reach Mars, likely due to this power issue or a failure in its radio system. Zond 2 silently passed by Mars on August 6, 1965, at an estimated distance of about 1,500 kilometers, but it was unable to transmit any data or images back to Earth. The mission is thus considered a failure, though it represented an important step in the Soviet space program's ambitions. In 1964, NASA embarked on its own attempt to conduct a flyby of Mars with the Mariner 3 mission. This mission was designed to expand upon the knowledge gained from earlier flyby attempts, providing more detailed images and data of the Martian surface and atmosphere. However, Mariner 3 encountered a critical failure shortly after launch. The issue stemmed from a faulty payload fairing, the protective covering that shields the spacecraft during launch. This fairing failed to properly jettison, preventing the deployment of Mariner 3's solar panels. Without these panels, the spacecraft was unable to generate the necessary power to operate its systems and maintain its trajectory. As a result, Mariner 3 failed to achieve its intended flyby of Mars. This failure, while disappointing, highlighted the importance of meticulous engineering and testing in space missions. The experience gained from Mariner 3's failure contributed to improvements in payload fairing design and deployment mechanisms, ensuring greater reliability for future NASA missions. While 1964 saw the setback of Mariner 3, NASA's perseverance was rewarded with the monumental success of Mariner 4. This mission, launched in the same year, achieved a historic first, a successful flyby of Mars. Mariner 4's accomplishment marked a watershed moment in our understanding of the Red Planet, delivering the first ever close-up images of its surface. On July 14, 1965, Mariner 4 transmitted 21 images back to Earth. These images revealed a heavily cratered surface, strikingly similar to that of the Moon. This discovery dramatically altered prevailing scientific assumptions about Mars, which had previously been envisioned as a potentially Earth-like world. The cratered terrain suggested a much older and more geologically inactive planet than previously thought. Mariner 4's groundbreaking images and data revolutionized our perception of Mars, paving the way for future, more sophisticated missions to explore its mysteries. In 1969, NASA continued its exploration of Mars with the Mariner 6 and Mariner 7 flyby missions. These missions represented a significant advancement in our understanding of the Red Planet, building upon the earlier successes of Mariner 4. Unlike their predecessor, these spacecraft were equipped with improved instruments, allowing them to capture more detailed images and gather more comprehensive data about Mars. Mariner 6 and 7 performed close flybys of Mars, providing a closer look at the planet's surface and atmosphere. The images returned by these missions revealed a heavily cratered terrain, confirming and expanding upon the observations made by Mariner 4. These missions also provided valuable data about the Martian atmosphere, including its composition and temperature. The information gathered from Mariner 6 and 7 played a crucial role in refining our understanding of Mars's geological features and atmospheric properties. Mariner 8, launched in 1971, failed during launch. The goal was to orbit the red planet, collect data on its atmosphere, surface, and environmental conditions, and transmit this information back to Earth. This mission was part of a broader effort to understand Mars in greater detail, building on earlier fly-by missions like Mariner 4, 6, and 7. Unfortunately, Mariner 8 never reached its destination. Shortly after launch, the mission encountered a catastrophic failure. The Atlas Centaur rocket, tasked with carrying the spacecraft into space, experienced a malfunction in its upper stage. Approximately 365 seconds into the flight, the Centaur stage's guidance system failed, causing the rocket to lose stability and tumble out of control. 1971 was a pivotal year. The Soviet Cosmos 419, an orbiter attempt, failed to leave Earth orbit. Its primary objective was to enter orbit around Mars and serve as a communication relay, supporting the upcoming lander and orbiter missions by ensuring robust data transmission back to Earth. It was carried into space by a Proton K rocket equipped with a Block D upper stage, a configuration commonly used for interplanetary missions. The trouble arose when the Block D stage failed to ignite properly for its second burn, which was necessary to propel Cosmos 419 out of Earth orbit and onto a trajectory toward Mars. Investigations later revealed that the failure stemmed from a human error. The timer for the ignition sequence had been incorrectly set to 1.5 days instead of the intended 1.5 hours. The Soviet Union launched Mars 2 and Mars 3 in 1971 as part of an ambitious effort to explore the Red Planet. These missions were notable for their dual design, each featuring both an orbiter to study Mars from above and a lander to investigate the surface directly. They represented a bold step in space exploration during the Cold War era. Unfortunately, Mars 2's lander met a harsh fate, crashing into the Martian surface upon arrival due to a failure during its descent. In contrast, Mars 3 marked a historic achievement when its lander executed the first successful soft landing on Mars on December 2, 1971. However, the lander's success was fleeting. It transmitted data for just 20 seconds before mysteriously shutting down, possibly overwhelmed by a dust storm. Despite the lander's mixed results, the orbiters of both Mars 2 and Mars 3 performed more reliably. Circling the planet, they gathered and sent back valuable data about Mars' atmosphere, surface features, and environmental conditions. This information, though limited, offered scientists an early glimpse into the mysteries of Mars. NASA's Mariner 9 marked a historic milestone as the first spacecraft to successfully enter orbit around Mars, a feat that opened new chapters in planetary exploration. Launched in 1971, it reached the Red Planet during an unexpected and massive global dust storm that initially shrouded much of the surface in a hazy veil. This swirling tempest delayed clear observations, keeping scientists in suspense as they awaited glimpses of Mars's hidden terrain. As the dust gradually settled, Mariner 9 began transmitting stunning images back to Earth, unveiling a world far more dynamic than previously imagined. The spacecraft revealed towering volcanic features, including the colossal Olympus Mons, the largest volcano in the solar system, standing nearly 3 times the height of Mount Everest. Its cameras also captured vast canyons, such as the sprawling Valles Marineris, a rift so immense it dwarfs Earth's Grand Canyon, stretching over 2,500 miles across the Martian landscape. These discoveries reshaped our understanding of Mars, painting a picture of a planet with a dramatic geological past. Mariner 9's extended mission, lasting nearly a year, provided a wealth of data that fueled decades of scientific study. By piercing through the storm's chaos, it laid the groundwork for future explorations, proving that Mars held secrets as grand as its newly revealed landscapes. In 1973, the Soviet Union embarked on an ambitious dual mission to explore Mars, launching 2 spacecraft, Mars 4 and Mars 5, as part of their ongoing efforts to unlock the mysteries of the Red Planet. Mars 4 was designed to orbit Mars, but it encountered technical difficulties that prevented it from slowing down and entering orbit as hoped. Instead, it sailed by, offering only a fleeting glimpse of Mars before continuing into the depths of space. Meanwhile, Mars 5 proved more successful, achieving what its sibling could not by slipping into orbit around Mars after its launch in July 1973. Once in place, it began diligently collecting and transmitting valuable data back to Earth, providing Soviet scientists with a trove of information about the planet's atmosphere and surface. Its instruments captured images and measurements, revealing details about Mars's thin atmosphere and its rugged cratered terrain during its operational lifespan. Though the missions had mixed outcomes, Mars 5's success stood as a testament to Soviet engineering, contributing to the global understanding of Mars at a time when space exploration was fiercely competitive. The spacecraft operated for several weeks before succumbing to technical issues, but not before enriching the growing body of knowledge about our planetary neighbor. In 1973, the Soviet Union continued its bold push to conquer Martian exploration with the launches of Mars 6 and Mars 7, 2 spacecraft designed to achieve the ambitious goal of landing on the red planet's surface. Unlike their predecessors focused on orbiting or flybys, these missions aimed to deliver landers that could directly study Mars up close. Both were equipped with instruments to collect data as they plunged through the Martian atmosphere, offering a rare chance to probe its mysteries during descent. Mars 6, launched in August 1973, successfully transmitted atmospheric data as it descended, providing scientists with valuable insights into the planet's thin, carbon dioxide-rich envelope. However, the mission took a frustrating turn when contact was abruptly lost just moments before it was expected to touch down, leaving its fate uncertain and robbing researchers of surface data. The brief stream of information it sent back was a tantalizing tease, hinting at what might have been. Similarly, Mars 7 faced its own challenges after its launch later that month, managing to relay some atmospheric readings during its rapid fall toward Mars. Yet, like Mars 6, it too fell silent before reaching the surface, its signal vanishing due to a trajectory error that caused it to miss the planet entirely and drift into space. These twin disappointments highlighted the immense difficulties of landing on Mars, but the atmospheric snippets they provided added incrementally to the growing mosaic of knowledge. In 1975, NASA took a monumental leap in Mars exploration by launching Viking 1 and Viking 2, 2 sophisticated missions that paired orbiters with landers to study the red planet in unprecedented detail. These twin spacecraft were designed to work in tandem. The orbiters would map Mars from above, while the landers would touch down to investigate the surface directly. After their journeys through space, Viking 1 made history by landing on July 20, 1976, followed by Viking 2 on September 3, 1976, each touching down in different regions to broaden the scope of exploration. From their vantage points in orbit, the Viking spacecraft captured thousands of high-resolution images, revealing Mars' dramatic landscapes, craters, volcanoes, and vast plains, in striking clarity. On the ground, a lander snapped the first close-up photographs of the rusty, rock-strewn terrain and conducted groundbreaking experiments to search for signs of microbial life, analyzing soil samples for chemical hints of biological activity. Though the results were inconclusive, sparking debate for years, they marked a pioneering effort in astrobiology. The missions proved remarkably durable, with Viking 1 operating until 1982 and Viking 2 until 1980, far exceeding initial expectations. During their years of service, they amassed a wealth of data about Mars' atmosphere, weather patterns, and geology, transforming our understanding of the planet. The Viking program's success set a high bar for future missions, cementing NASA's reputation in interplanetary exploration and leaving a lasting legacy of discovery that fueled curiosity about life beyond Earth. In 1988, the Soviet Union set its sights beyond Mars itself, launching Phobos 1 and Phobos 2 with the ambitious goal of studying Phobos, the larger of the red planet's two moons. These missions were part of a broader effort to understand the Martian system, with plans to analyze Phobos' composition, orbit, and surface features up close. Both spacecraft were equipped with advanced instruments, and Phobos 2 even carried a small lander intended to touch down on the moon's cratered terrain, marking a daring new frontier in exploration. Unfortunately, Phobos 1's journey ended prematurely due to a devastating software error shortly after its launch in July 1988. A misinterpreted command from ground control caused the spacecraft to shut down its orientation system, leaving it tumbling helplessly and unable to communicate with Earth. The loss was a bitter blow to the Soviet team, snuffing out its chance to contribute to the mission's objectives before it even reached Mars' vicinity. Phobos 2, launched days later, fared slightly better, successfully reaching Martian orbit in early 1989 and beginning its study of Phobos. It managed to send back a handful of images and some data about the moon's surface and the Martian atmosphere before disaster struck again. Just as it was preparing to deploy its lander, contact was lost in March 1989, likely due to a failure in its onboard systems. Though both missions ultimately fell short, Phobos 2's brief transmissions offered tantalizing clues about Phobos, stoking curiosity about this mysterious moon, despite the setbacks. In September 1992, NASA launched the Mars Observer, an advanced orbiter designed to conduct a comprehensive study of the red planet from above, marking a significant step in the agency's ongoing exploration efforts. The spacecraft was packed with cutting-edge instruments to map Mars' surface in fine detail, monitor its weather patterns, and analyze its atmosphere and geological features over an extended mission. After a nearly year-long journey, it was poised to enter Martian orbit in August 1993, promising a wealth of new insights into the planet's mysteries. Tragically, the mission took a devastating turn just 3 days before it was scheduled to begin orbiting Mars. On August 21, 1993, contact with Mars Observer was abruptly lost during a routine procedure to pressurize its fuel tanks, a critical step for orbital insertion. Despite exhaustive attempts to re-establish communication, the spacecraft remained silent, leaving NASA scientists and engineers grappling with the sudden and unexplained failure of a highly anticipated project. The loss of Mars Observer was a major setback, with speculation pointing to a possible explosion or propulsion malfunction as the cause, though no definitive answer ever emerged. Costing hundreds of millions of dollars, the mission's failure stung deeply, but its ambitious goals weren't abandoned entirely. NASA later repurposed much of its technology and objectives into future missions, ensuring that the Mars Observer's legacy lived on. In November 1996, NASA launched the Mars Global Surveyor, an orbiter that would go on to become one of the most successful missions in the agency's history of Martian exploration, operating until 2006. Designed to pick up where earlier efforts left off, this spacecraft was equipped with a suite of advanced instruments, including a high-resolution camera, a laser altimeter, and tools to study the planet's atmosphere. Arriving in Martian orbit in September 1997, after a 10-month journey, it quickly began delivering a treasure trove of data that transformed our view of the red planet. Over its nearly decade-long mission, Mars Global Surveyor captured stunningly detailed images of Mars' surface, revealing features as small as a few meters across, craters, dunes, and volcanic landscapes in crisp clarity. Its laser altimeter mapped the planet's topography with precision, creating 3D models that highlighted dramatic elevation changes, like the towering Tharsis volcanoes and the deep Valles Marineris. Perhaps most excitingly, it uncovered compelling evidence of past liquid water, spotting ancient riverbeds, gullies, and mineral deposits that suggested Mars once had flowing streams or even oceans. The orbiter's longevity allowed it to monitor seasonal changes, track dust storms, and even assist later missions by scouting landing sites, all while beaming back data until its sudden silence in November 2006, likely due to battery failure. Mars Global Surveyor's findings reshaped scientific understanding, bolstering theories about Mars' wetter past and setting the stage for future quests to explore its potential for life. Its remarkable run cemented its place as a cornerstone of planetary science. In November 1996, Russia launched the Mars 96 mission, an ambitious endeavor spearheaded by the Russian Space Forces to explore the Red Planet with an orbiter, 2 landers, and 2 surface penetrators. This spacecraft, launched on November 16 from the Baikonur Cosmodrome in Kazakhstan, atop a Proton K rocket, was intended to investigate Mars' atmosphere, surface, and interior, building on lessons learned from earlier Soviet attempts, like the Phobos missions. However, the mission met a swift and unfortunate end due to a catastrophic failure during its launch phase, preventing it from ever reaching its intended destination. The trouble began shortly after liftoff, when the Proton K rocket successfully placed Mars 96 into a low Earth orbit. The plan relied on the Block D2 upper stage to execute a second burn to propel the spacecraft toward Mars, but this crucial step faltered. The fourth stage failed to ignite properly, leaving the spacecraft stranded in an unstable orbit. Despite separating from the upper stage and attempting its own engine burn, Mars 96 couldn't overcome the initial setback. Within hours, it succumbed to Earth's gravity, re-entering the atmosphere on November 17, 1996, and disintegrating over a wide swath that included parts of the Pacific Ocean, Chile, and Bolivia. The mission's failure was a significant blow to Russia's space program, especially as Mars 96 carried a hefty payload of scientific instruments, some contributed by international partners like France, Germany, and the United States, and 200 grams of plutonium-238 for power generation. The exact cause of the launch mishap remains uncertain, with investigations hampered by a lack of telemetry data during key moments, pointing to either a flaw in the Proton K's upper stage or a malfunction in the spacecraft itself. Though its debris scattered across a remote region, the loss of Mars 96 underscored the persistent challenges of Mars exploration and marked Russia's last planetary mission of the 20th century. Mars Pathfinder was a NASA mission launched on December 4, 1996, aimed at demonstrating a cost-effective method for delivering scientific instruments and a rover to the Martian surface. Its primary goals were to land a stationary spacecraft on Mars, deploy the Sojourner rover, the first wheeled vehicle to operate on another planet, and study the planet's geology, atmosphere, and climate. The lander, equipped with cameras and a weather station, was designed to analyze the Martian environment, while Sojourner, a small 10.6-kilogram rover, was tasked with examining rocks and soil near the landing site in Ares Vallis, an ancient floodplain. The mission successfully touched down on July 4, 1997, using an innovative airbag landing system. Both the lander, renamed the Carl Sagan Memorial Station, and Sojourner exceeded expectations, operating for 83 days, nearly 3 times the planned 30-day mission duration. They returned over 17,000 images and extensive data, including evidence of past water activity, before contact was lost on September 27, 1997, likely due to battery failure in the lander. Mars Pathfinder was a resounding success, paving the way for future rover missions. In July 1998, Japan ventured into deep space exploration with the launch of Nozomi, a modest yet ambitious Mars orbiter developed by the Institute of Space and Astronautical Science, marking the country's first attempt to study another planet. Launched aboard an MV rocket from the Kagoshima Space Center, Nozomi, meaning hope in Japanese, was designed to investigate Mars' upper atmosphere, magnetic field, and interactions with the solar wind, carrying a suite of 14 scientific instruments, some contributed by international partners like Canada and Germany. However, its 5-year journey was plagued by technical setbacks that ultimately prevented it from achieving its goal of orbiting the red planet. The troubles began early during a critical Earth flyby in December 1998 intended to slingshot Nozomi toward Mars. A malfunction in a valve controlling its thruster caused the spacecraft to use far more fuel than planned, leaving it on a suboptimal trajectory. Mission controllers devised a backup plan, extending its voyage with additional Earth flybys in 2002 and 2003 to conserve fuel and adjust its path, delaying its arrival at Mars from 1999 to December 2003. Despite these efforts, Nozomi faced another crippling blow when solar flares in April 2002 damaged its electrical systems, impairing its communication and propulsion capabilities. By the time Nozomi approached Mars in December 2003, its team made a last-ditch attempt to fire its engines and enter orbit, but the spacecraft's thrusters failed to respond, likely due to the earlier solar damage or frozen fuel lines. On December 9, 2003, Japan's space agency reluctantly abandoned the mission, directing Nozomi to bypass Mars entirely and drift into a heliocentric orbit around the Sun. Though it never fulfilled its scientific objectives, Nozomi's challenging journey provided valuable lessons for Japan's fledgling planetary program, paving the way for future successes like the Akatsuki Venus Orbiter. In December 1998, NASA launched the Mars Climate Orbiter, a spacecraft designed to study the Martian atmosphere, weather patterns, and surface changes as part of the agency's renewed push to explore the red planet following the Mars Observer loss. Launched atop a Delta II rocket from Cape Canaveral, the orbiter was meant to complement the Mars Global Surveyor by focusing on climate dynamics, tracking water vapor, dust, and temperature variations from orbit. After a smooth 9-month journey, it arrived at Mars in September 1999, poised to settle into a precise orbit, but a stunningly simple error brought the mission to a catastrophic end. The failure stemmed from a navigation blunder caused by a mismatch between measurement systems. Lockheed Martin, which built the spacecraft, provided thruster data in English units, pound-seconds, while NASA's Jet Propulsion Laboratory expected metric units, Newton-seconds. This miscommunication went unnoticed during the mission, skewing the trajectory calculations. On September 23, 1999, as the orbiter fired its engines to enter Mars orbit, it dipped too low into the atmosphere, about 57 kilometers above the surface, instead of the planned 140-150 kilometers, where it likely burned up or broke apart under the intense heat and pressure. Contact was lost just minutes after the maneuver, and subsequent investigations confirmed the unit conversion error as the culprit, costing NASA a $125 million mission. The loss of the Mars Climate Orbiter became a high-profile embarrassment, prompting widespread scrutiny of the agency's processes and overhaul of its quality control measures. Though it never transmitted the climate data it was built to collect, the incident underscored the critical importance of precision in spaceflight and left a cautionary tale that echoed through NASA's later, more successful Mars endeavors. In January 1999, NASA launched the Mars Polar Lander paired with the Deep Space 2 mission, an innovative duo aimed at exploring Mars' southern polar region and testing new technologies for planetary landings. The Mars Polar Lander, launched atop a Delta II rocket from Cape Canaveral, was designed to touch down near the planet's south pole to study its layered terrain, search for water ice, and monitor local weather, equipped with a robotic arm and cameras. Riding along were Deep Space Two's two tiny microprobes, Amundsen and Scott, each about the size of a basketball, intended to piggyback on the lander's descent and slam into the surface at high speed to penetrate the soil and analyze subsurface water content. After an uneventful 11-month journey, the spacecraft arrived at Mars on December 3, 1999, initiating their descent toward the icy polar landscape. The plan was for the lander to separate from its cruise stage, use retrorockets to softly touch down, and release the microprobes to burrow into the ground moments before impact. However, all three components, the lander and both probes, vanished without a trace during this critical phase. The last signal from the Mars polar lander came just before it entered the atmosphere, and no communication was ever established with Deep Space 2, leaving their fates a mystery. Investigations later pointed to a likely software flaw in the lander's descent system. Its engines may have shut off prematurely when a sensor misinterpreted vibrations as a landing, causing it to plummet fatally to the surface from about 40 meters up. The microprobe's loss remains less clear, possibly due to their experimental design failing under the harsh impact or communication issues. Costing $165 million combined, the twin failures stung NASA, especially coming on the heels of the Mars Climate Orbiter loss, but they spurred improvements in testing and redundancy. Mars Odyssey, launched in 2001, stands as a testament to the longevity and productivity of NASA's planetary exploration. This orbiter, designed to map the Martian surface and analyze its composition, achieved a landmark discovery: substantial evidence of subsurface water ice. This revelation significantly altered our understanding of Mars's potential habitability, hinting at a frozen reservoir beneath the arid landscape. Beyond its initial breakthrough, Mars Odyssey has continued to serve as a crucial communications relay for rovers on the Martian surface, acting as a vital link to Earth. The orbiter's ongoing operation allows for continuous monitoring of the planet's environment, tracking seasonal changes, and providing invaluable data on the distribution of water ice. This sustained observation contributes to a deeper understanding of Mars's dynamic climate and geological processes. Even after decades in orbit, Mars Odyssey remains a workhorse, delivering scientific data that informs future missions and shapes our perception of the red planet. Its enduring mission highlights the importance of long-term planetary observation, proving that consistent data collection is essential for unraveling the mysteries of distant worlds. The information gathered by Odyssey continues to be fundamental for the planning and execution of future human and robotic exploration efforts. The European Space Agency's Mars Express, launched in 2003, embarked on a mission to comprehensively characterize the Martian environment. This sophisticated orbiter, equipped with a suite of advanced instruments, has delivered a treasure trove of high-resolution images, revealing the intricate details of Mars's diverse geological features. From towering volcanoes to deep canyons, Mars Express has painted a vivid portrait of the red planet's surface, providing crucial context for understanding its past and present. Furthermore, Mars Express has played a pivotal role in the search for water on Mars, providing strong evidence of subsurface water ice. Utilizing its Marsus radar, the orbiter has peered beneath the planet's surface, detecting signals consistent with frozen water deposits. This discovery reinforces the idea that Mars once possessed, and may still possess, significant quantities of water, a key ingredient for life. Additionally, the orbiter's detection of methane in the Martian atmosphere has sparked intense scientific debate, as methane can be a byproduct of both geological and biological processes. Despite its long tenure, Mars Express continues to operate effectively, providing ongoing data that refines our understanding of Mars. Its persistent monitoring of the Martian atmosphere and surface contributes to a dynamic picture of the planet's evolving environment. The accumulated data, from detailed imagery to atmospheric composition measurements, remains essential for planning future exploration missions and unraveling the mysteries of this fascinating world. The enduring success of Mars Express underscores the value of international collaboration in planetary science. Beagle 2, launched in 2003 by the European Space Agency, represented a bold attempt to land a small, innovative probe on Mars. This mission was part of European Space Agency's Mars Express Orbiter project, with Beagle 2 designed to conduct surface and subsurface investigations. Its primary goal was to search for signs of past or present life on the Red Planet, a question that has captivated scientists for decades. Unfortunately, Beagle 2's fate took a tragic turn during its descent. After successfully separating from the Mars Express orbiter, communication with the lander was lost. Despite extensive efforts to re-establish contact, no signals were received. It was later determined that the lander had likely reached the Martian surface, but a failure in its deployment sequence prevented it from transmitting data back to Earth. This loss marked a significant setback for European Space Agency's Mars exploration program. The Mars Exploration Rover mission, featuring Spirit and Opportunity, launched in 2003, stands as a testament to NASA's remarkable engineering and scientific prowess. These twin rovers were designed for a mere 90-day mission, but they far exceeded expectations, revolutionizing our understanding of Mars. Spirit and Opportunity's primary objective was to search for and characterize a wide range of rocks and soils that held clues to past water activity on Mars. They landed in different Martian hemispheres, each equipped with instruments to analyze the composition and texture of the Martian terrain. Spirit, landing in Gusev crater, discovered evidence of ancient hydrothermal systems, suggesting a warmer, wetter past. However, in 2009, Spirit became trapped in a sandpit, hindering its ability to reposition its solar panels, and ultimately leading to the cessation of communication in 2010. Opportunity, landing in Meridiani Planum, uncovered conclusive evidence of past liquid water, including hematite spherules nicknamed blueberries and layered sedimentary rocks. This rover's remarkable longevity allowed it to traverse vast distances, exploring numerous craters and providing invaluable data. Opportunity continued to operate until 2018, when a massive dust storm engulfed Mars, blocking sunlight and preventing the rover from recharging its batteries. Its demise, though poignant, marked the end of an extraordinary era of Martian exploration. The Mars Reconnaissance Orbiter, MRO, launched in 2005 by NASA, is a cornerstone of Martian exploration, providing an unparalleled view of the Red Planet. This highly sophisticated spacecraft has been instrumental in deepening our understanding of Mars's complex geology, climate, and potential for past or present habitability. MRO's suite of advanced instruments allows it to capture incredibly detailed images of the Martian surface, revealing features as small as a dinner table. Its high-resolution imaging science experiment, HiRISE camera, in particular, has produced stunning visuals that have revolutionized our perception of Mars. Beyond its imaging capabilities, MRO also carries instruments that analyze the composition of the Martian surface and subsurface, detecting minerals and searching for evidence of water ice. One of its most important functions is to provide data relay services, acting as a crucial communication link between surface missions, such as rovers and landers, and Earth. This interplanetary internet capability is essential for the successful operation of these missions. Furthermore, MRO plays a vital role in identifying and characterizing potential landing sites for future Mars missions. By providing detailed maps and analyzing the terrain, it helps ensure the safety and success of these endeavors. This ongoing mission continues to deliver valuable scientific data, contributing significantly to our quest to unravel the mysteries of Mars. The Phoenix Mars lander, launched by NASA in 2007, was a specialized mission designed to investigate the Martian Arctic region. Its primary objective was to analyze the history of water in the Martian polar ice and to assess the potential habitability of the icy soil. Phoenix landed in the northern polar region of Mars, a location chosen for its known abundance of subsurface water ice. Equipped with a robotic arm, the lander excavated samples of the Martian soil and delivered them to its onboard instruments for analysis. A key achievement of the mission was the definitive confirmation of water ice just beneath the surface. This discovery provided crucial evidence of water's presence in the Martian Arctic, a finding that has significant implications for understanding the planet's past and present climate. In addition to confirming water ice, Phoenix also analyzed the chemical composition of the soil, revealing the presence of perchlorates and other compounds. While the mission was designed to operate for a limited period, it provided valuable insights into the Martian Arctic environment. As the Martian winter approached, the lander's solar panels were no longer able to generate sufficient power, and communication with Earth was lost in 2008. Despite its relatively short operational lifespan, the Phoenix mission significantly advanced our understanding of Mars's polar regions and the distribution of water on the planet. NASA's Curiosity rover, a marvel of modern engineering, embarked on its mission to Mars in 2011, landing successfully in Gale Crater in August 2012. This car-sized rover, part of the Mars Science Laboratory mission, was designed to investigate whether Mars ever possessed the environmental conditions to support microbial life. Its primary objective is to analyze the Martian rocks and soil, searching for clues that would reveal the planet's past habitability. Curiosity's landing in Gale Crater was a feat of precision, employing a complex sky crane maneuver to gently lower the rover onto the Martian surface. Equipped with a sophisticated suite of scientific instruments, Curiosity is essentially a mobile laboratory. It carries tools that can drill into rocks, analyze their chemical composition, and even vaporize small portions of rock with a laser to determine their makeup. One of Curiosity's key discoveries has been the confirmation that Gale Crater once hosted an ancient lake system, providing evidence of a past environment that could have supported microbial life. The rovers found organic molecules and other chemical signatures that suggest the presence of past habitable conditions. As it continues its journey up Mount Sharp, the central peak within Gale Crater, Curiosity is exploring different layers of Martian history, seeking to understand how the planet's environment has changed over billions of years. Crucially, Curiosity is still an active rover, continuing to transmit valuable data back to Earth. Its ongoing exploration provides scientists with a wealth of information about Mars's geology, climate, and potential for past or present life. The data that it gathers is vital in preparing for future human exploration of the Red Planet. The Phobos Grunt mission, launched by Russia in 2011, represented an ambitious attempt to retrieve soil samples from Phobos, one of Mars's moons. This mission was designed to provide valuable insights into the composition and origin of Phobos, and potentially shed light on the early history of the solar system. However, the mission was ultimately unsuccessful, failing to achieve its intended trajectory. It failed to leave Earth orbit due to a propulsion issue and re-entered in January 2012. Yinghuan, launched in 2011, represented China's ambitious first foray into Mars exploration. This orbiter, designed to study the Martian environment, was a crucial component of a joint mission with Russia's Phobos Grunt spacecraft. Unfortunately, the mission encountered a critical failure shortly after launch, preventing Yinghuan from reaching its intended destination. The orbiter was designed to gather data on Mars's magnetic field, ionosphere, and the interaction between the solar wind and the Martian atmosphere. The joint launch with Phobos Grunt meant both missions shared a common fate, as the Russian spacecraft also experienced a fatal malfunction, leaving both payloads stranded in Earth orbit. MAVEN, the Mars Atmosphere and Volatile Evolution mission, launched by NASA in 2013, is a dedicated orbiter designed to unravel the mysteries of Mars's upper atmosphere. Its primary objective is to determine how and why Mars transitioned from a potentially warm and wet world to the cold, arid planet we observe today. By meticulously studying the atmospheric escape processes, MAVEN provides crucial insights into the planet's climate history, and therefore its potential to have hosted life. The spacecraft carries a suite of sophisticated instruments that measure the composition, structure, and dynamics of the Martian upper atmosphere. These measurements allow scientists to assess the rate at which atmospheric gases are being lost to space, particularly due to the solar wind. Furthermore, MAVEN has also served a critical role in relaying communications from the Martian surface back to Earth for other Mars missions. Having had its mission extended multiple times, MAVEN continues to provide invaluable data and is still actively contributing to our understanding of the Red Planet. The Mars Orbiter mission, also known as Mangalyaan, launched by the Indian Space Research Organization in 2013, marked a significant milestone in space exploration. This mission was India's first interplanetary endeavor, and it achieved the remarkable feat of successfully entering Martian orbit in 2014. Mangalyaan was designed to study the Martian atmosphere and surface, providing valuable scientific data. Specifically, Mangalyaan carried instruments to analyze the composition of the Martian atmosphere and to image the planet's surface features. What made this mission particularly impressive was its cost-effectiveness and its longevity. Originally intended to operate for a period of 6 months, Mangalyaan continued to function and transmit data for nearly 8 years, significantly exceeding its planned lifespan. This extended operation provided a wealth of information about Mars, further contributing to our understanding of the Red Planet. However, in 2022, ISRO lost contact with the Mangalyaan orbiter, bringing the successful mission to its conclusion. The ExoMars Trace Gas Orbiter, a collaborative mission between the European Space Agency and Roscosmos, launched in 2016, represents a dedicated effort to unravel the composition of the Martian atmosphere. Its primary focus is the precise measurement and analysis of trace gases, with a particular emphasis on methane. The presence of methane on Mars has long been a source of scientific intrigue, as it could potentially indicate geological or even biological activity. Beyond its atmospheric studies, the Trace Gas Orbiter also plays a crucial role as a communications relay for other Mars missions. This function is vital for maintaining contact with rovers and landers on the Martian surface, transmitting data back to Earth. The orbiter's suite of sophisticated instruments allows for detailed spectroscopic analysis, enabling scientists to identify and quantify the various trace gases present in the Martian atmosphere. With its extended mission, the ExoMars Trace Gas Orbiter continues to provide valuable data and remains an active and essential component of ongoing Mars exploration. The Schiaparelli Entry, Descent, and Landing Demonstrator Module, launched in 2016 as part of the ExoMars program, was a joint effort between the European Space Agency and Roscosmos. Its primary objective was to test and validate the technologies necessary for a controlled landing on Mars. This mission was a crucial step towards future European Mars landers and rovers. Schiaparelli's descent was designed to gather data on the Martian atmosphere during entry, providing valuable information for future landing attempts. However, during the final stages of its descent, a critical malfunction occurred. Premature release of the parachute and a brief activation of the braking thrusters resulted in the lander impacting the Martian surface at a high velocity. While the landing was unsuccessful, the mission provided valuable data about the entry and descent phase, aiding in the development of more robust landing systems for future Mars missions. Despite its crash, Schiaparelli served as an important, albeit costly, learning experience. InSight, short for Interior Exploration Using Seismic Investigations, Geodesy and Heat Transport, was a NASA lander that touched down on Mars in 2018. Unlike previous missions that focused on the Martian surface or atmosphere, InSight was designed to peer deep into the planet's interior, Its primary mission was to gather data about Mars's seismic activity, heat flow, and overall internal structure, providing insights into the formation and evolution of terrestrial planets. The lander carried two primary instruments: a seismometer to detect Marsquakes and a heat flow probe to measure the planet's internal temperature. These instruments provided unprecedented data about the Martian mantle and core, revealing details about the planet's composition and geological processes. InSight operated successfully for several years, detecting numerous Marsquakes and providing valuable information about the planet's thermal history. However, as Martian dust accumulated on its solar panels, the lander's power generation gradually decreased. In 2022, NASA declared the mission concluded, as InSight could no longer generate sufficient power to operate its instruments, marking the end of a groundbreaking mission that unveiled the hidden secrets of Mars's interior. NASA's Perseverance rover, launched in 2020, represents a pivotal step in the search for past life on Mars. Its landing site, Jezero Crater, is a former lakebed, chosen for its potential to contain evidence of ancient microbial life. Perseverance's primary mission is to explore this geologically rich area, collecting carefully selected rock and soil samples for future return to Earth. Equipped with a suite of advanced instruments, Perseverance analyzes the Martian geology and searches for signs of past habitability. Notably, it carries a drill and sample catching system, allowing it to collect and store samples in sealed tubes. These samples are intended to be retrieved by a future mission, bringing them back to Earth for detailed laboratory analysis. Beyond sample collection, Perseverance also deployed the Ingenuity helicopter, a technology demonstration that has proven the feasibility of powered flight on Mars. The rover continues to traverse Jezero Crater, providing stunning images and valuable scientific data, and remains an active and crucial component of NASA's Mars exploration program. Ingenuity, a small solar-powered helicopter, made history in 2021 by achieving the first powered, controlled flight on another planet. It was deployed from the belly of NASA's Perseverance rover, which landed in Jezero Crater. Initially conceived as a technology demonstration, Ingenuity's primary goal was to prove that flight was possible in Mars's thin atmosphere. The helicopter's success far exceeded expectations. After its initial test flights, Ingenuity transitioned into an operational role, serving as an aerial scout for the Perseverance rover. Its flights provided valuable reconnaissance, helping the rover team identify potential routes and interesting geological features. Ingenuity's ability to capture high-resolution images from an aerial perspective has significantly enhanced the rover's exploration capabilities. On January 18, 2024, during Flight 72, a rotor blade broke off and other blade tips were damaged, resulting in Ingenuity's permanent grounding. On January 25, 2024, NASA Administrator Bill Nelson announced the end of the mission. However, Ingenuity will remain on Mars as an inactive artifact, with its stored climate and atmospheric data potentially retrievable in the future. Tianwen-1, launched by China in 2020, stands as a landmark achievement in Mars exploration. This ambitious mission encompassed an orbiter, a lander, and the Zhurong rover, demonstrating China's comprehensive approach to studying the Red Planet. Its successful landing in Utopia Planitia in 2021 marked China as the second nation to achieve a soft landing on Mars. The Zhurong rover, deployed from the lander, explored the Martian surface, gathering data about the planet's geology and searching for evidence of past water. Its instruments have provided valuable insights into the composition of Martian rocks and soil, as well as the planet's subsurface structure. Meanwhile, the Tianwen-1 orbiter continues to circle Mars, conducting remote sensing observations and relaying data from the rover back to Earth. This multifaceted approach has allowed for a thorough investigation of Mars, contributing significantly to our understanding of its history and potential for habitability. The mission is still active and continues to send back valuable scientific data. However, the Zhurong rover lost contact in 2023 after failing to awake from a scheduled hibernation. The Hope Mars mission, also known as Al-Amal, launched by the United Arab Emirates in 2020, represents a significant milestone for the Arab world's space exploration efforts. This orbiter's primary mission is to provide a comprehensive understanding of the Martian atmosphere, specifically its dynamics and interactions with the solar wind. Hope's unique orbital path allows it to capture a global view of Mars, providing a complete picture of the atmospheric circulation and weather patterns. Its suite of advanced instruments measures the distribution of key atmospheric constituents, such as hydrogen and oxygen, and studies how these elements escape into space. By tracking these processes, Hope is helping scientists understand the long-term evolution of the Martian atmosphere and how it has changed over time. The mission is actively collecting valuable data and has contributed a wealth of information to the scientific community, further enhancing our knowledge of the Red Planet. The ExoMars Rosalind Franklin rover, currently planned for launch in 2028, is a highly anticipated mission designed to directly address the question of whether life ever existed on Mars. A joint project between the European Space Agency and Roscosmos, this rover is named after Rosalind Franklin, the pioneering DNA researcher. Its primary objective is to search for organic molecules and other potential biosignatures beneath the Martian surface. Unlike previous rovers that have primarily explored the surface, the Rosalind Franklin rover is equipped with a powerful drill capable of reaching depths of up to 2 meters. This capability will allow it to access subsurface regions that are shielded from the harsh radiation and oxidizing conditions on the Martian surface, where evidence of past or present life may be better preserved. The rover's onboard laboratory will analyze collected samples, searching for the chemical building blocks of life. If successful, this mission could provide definitive evidence of extraterrestrial life, or at least establish the conditions necessary for its emergence. Due to the geopolitical situation, the Roscosmos participation is currently suspended, and the European Space Agency is working on finding alternative solutions to launch in 2028. The Mars Sample Return Mission represents an ambitious multi-stage endeavor by NASA and the European Space Agency, aiming to bring Martian samples back to Earth for detailed analysis. This mission builds upon the groundwork laid by the Perseverance rover, which is currently collecting and catching rock and soil samples within Jezero crater. The Mars Sample Return Mission is envisioned as a complex sequence of events. First, a sample retrieval lander will be sent to Mars. This lander will deploy a sample fetch rover, which will retrieve the sample tubes left behind by Perseverance. Then, a Mars ascent vehicle, launched from the lander, will carry the samples into Martian orbit. Finally, an Earth return orbiter will rendezvous with the orbiting samples, capture them, and transport them back to Earth. The return samples will be subjected to rigorous analysis in state-of-the-art laboratories, allowing scientists to conduct investigations that are not possible on Mars. This will provide unprecedented insights into the planet's geology, history, and potential for past or present life. The Mars Sample Return Mission is a complex undertaking requiring precise coordination and advanced technology, but its potential scientific rewards are immense, promising to revolutionize our understanding of the Red Planet. The Martian Moon's Exploration (MMX) mission, spearheaded by the Japan Aerospace Exploration Agency (JAXA) and planned for launch in 2026, is a pioneering endeavor focused on unraveling the mysteries of Mars's 2 moons, Phobos and Deimos. Unlike missions targeting Mars itself, MMX will concentrate on these intriguing celestial bodies, particularly Phobos. The mission's primary objective is to conduct detailed observations and sample collection from Phobos. The spacecraft will perform close flybys of both moons, gathering data on their composition, structure, and orbital characteristics. Critically, it will also attempt to land on Phobos and collect surface samples, which will then be returned to Earth for thorough analysis. Scientists believe that Phobos and Deimos may hold clues to the early solar system, potentially being captured asteroids or fragments of Mars ejected by a massive impact. The return samples from Phobos are expected to provide invaluable insights into the origin and evolution of these moons, and possibly shed light on the early history of Mars itself. The MMX mission is a significant step in expanding our understanding of the Martian system and the broader solar system. Mars is more than just a planet. It's a mirror, reflecting our own aspirations, our own fears, our own dreams. It's a testament to the power of human curiosity, the relentless drive to explore the unknown. The journey to Mars is a journey of discovery, a journey of self-discovery. It's a journey that will continue to inspire us, to challenge us, to push us to the very limits of our capabilities. We stand on the threshold of a new era of Martian exploration, an era where we may finally answer the age-old question, are we alone? The answers lie hidden in the Martian dust, waiting to be revealed. And as we continue to reach for the stars, we carry with us the hopes and dreams of all those who have dared to look up and wonder. The red planet beckons, a silent promise of discoveries yet to come. And we, as explorers, as scientists, as humans, will continue to answer that call. For in the exploration of Mars, we are not just exploring another world, we are exploring ourselves. Take care, and remember, there's a whole universe out there, just waiting for you to explore it.